In section 2.2, we are going to be talking about classification and regression, which are considered as supervised learning in machine learning. So supervised learning means that you have the known output. The output is known, meaning that it's labeled, and therefore it's called supervised learning. And there are two types of supervised learning. One is classification, the other is regression. So classification, as the name suggests, is to classify something. That means the outcome variable is going to be a categorical variable. It's going to be red or blue, 1, 2, right? Yes, no, right? Or it can be more than two class, meaning it can be red, blue, yellow, or orange, right? So that's considered as classification. So your target variable is categorical variable. And regression is considered as predicting a numerical variable. So what you're trying to predict is going to be a numerical value. So that's the differentiation between classification and regression. So let's get started. So as usual, we always use Scikit-learn. So Scikit-learn's, you can see that linear model, right? Import linear regression and logistic regression. Okay, so these are the two simplest models, right, that exist in Scikit-learn. So as the name suggests, linear regression is for regression, and logistic regression is for classification. So logistic regression, remember, is to predict a class, right, a categorical outcome, whereas linear regression is to predict something that's a numerical value, right? So, and then the second one is going to be Scikit-learn.svm. So this stands for support vector machine, and you can import SVC or SVR, right? So the first one stands for support vector classifier. The second one is support vector regressor. So as you can see that whenever you're trying to create a regression, it's always called regressor, right? The model is called regressor, and then whenever you're trying to classify something or create a classification model, the model is going to be called a classifier, right? So lastly, Scikit-learn.neighbors. So this is another type of big, I guess, category of models, right? So you can actually import k-means classifier, or k-means has, if you can just k-neighbors classifier. The other one is called k-neighbors regressor, right? For any model in Scikit-learn, typically you have a classifier as well as a regressor, right? That's kind of like, except for a linear model, the name is not so descriptive, because I mean this is very simple. Linear regression, you will know that it's a regression, but logistic regression, even though the name is regression, but it's a classification model, right? Remember that. So then let's use our data from before, right? So remember, like, our data is like, this is our data, right? We have bedrooms, bathrooms, and then rooms, square footage, lot size, year built, and prior sale amount, right? So we want to use these features, right, to predict something. Say we can now define our y. In our prior section, 2.1, we said that we didn't want to consider y because it's unsupervised learning. That means there is no y. There's no known outcome, right? However, in classification or regression, there is known outcome. So therefore, we want to consider x and y. And note that x is always like uppercase, right? So that means whenever you say uppercase, that's going to be a matrix. You know that's going to be a matrix. Whenever it's lowercase, it's going to be a vector array, meaning that it's only going to be one column, right? So you can actually do the same thing. So estimated value. So now we have x and y. So let's, just fit something quickly, right? The usual way is, because y, remember, is the estimated value, which is a numerical value, right? Y is a numerical value. So let's just, print out our y. You can see that's a numerical value, right? And then let's just ensure df.info to ensure that the type is actually saved in, right? It's an integer, right? So therefore, it's a numerical value. Okay, that's great. So now we can just say, we can actually initialize this model, right? In every model in Scikit-learn, you have to do this initialization statement, right? And then you can actually do fit, right? So fitting, you'll need to pass two things, right? In regression, because you need the feature. This is our feature matrix, right? We have 7 features, and then Y is our non-outcome, right? That's why it's called supervised learning, because you have the non-outcome, right? So you use 2 pieces of information to create this linear regression model, right? By using this function called .fit, right? So lg.fit, and then you can do lg.score. And then just put that. Okay, now the score is, 80, almost like 80%, right? 70, 76%. It's not that bad, right? But I'm thinking that it's going to be overfit. That means, so there's a concept in data science, overfitting, underfitting. So overfitting means that it's just going over, it's going after the noise, meaning if the model sees a new data set, it wouldn't perform as well, because this model is very, very specific to this data set that we use to train, right? So this part is the training, right? So therefore, we should do a train test split, right? So in Scikit-learn, luckily, there is a package that you can just use, right? It's called cross-validation. I think it's from cross-validation, right? It's from the cross-validation section of Scikit-learn, and then you can do train test split, right? Okay, awesome. So we can run this. And then, so before doing this, we should actually train test, split our x, y. If you don't put anything, the default is going to be 80% will go into training data set, and then 20% will go into test data set. But what you can do, what you will get are 4 things, right? So you're going to get x train, x test, y train, y test in this order. So you have to remember that's the order that Scikit-learn is defined by Scikit-learn, right? So now if we do this, right, you can actually look at the shape of it, the shape, and then say y train dot shape, right? Okay, so you can see that it's matching. So this is to say 1,250 records were routed into our training data set or used in our training data set, and the rest is going to be in the test data set, right? You can see the number of rows are actually matching between X train and Y train, as it should be, right? So now we can just pretty much copy over this thing, right? We don't want to use everything, the entire X and Y. We want to use train right in here. And then the score should be on test, right? Because you're going to fit the model. This is to fit or train, fit, right? And then this is to really evaluate. So you should have different data set, right, for that. So, or score, right? So let's see. Oh, interesting enough that it's actually better. It can happen. But the point here is that we want to really make sure that that this we do the train test split and then use train, X train, and Y train as to fit the data or to train the model, and then use X test and Y test to get the score. So this score is really just like in linear regression, it's the R, I'm sure you heard of this thing that's called R squared. So R squared is really just explained variance, right? How much variance in the target variable, in our case is estimated value, right, can be explained by the feature variance. So we have 7 features, right? By these features, we can explain pretty much 80% of the variance that is happening in our target variable. So this is actually considered as pretty okay model. Like 80% is kind of like the cutoff that you're saying. If it's above 80%, then I think that this model is, usable. It's good enough model. So this is how you can actually create a linear regression, right? So say we want to do, logistic regression. We want to create a logistic regression.